This is Lab 2, Motion of a Falling Object by Nicholas Schweiker. So for the introduction, the purpose of this lab is to analyze the effect of air resistance on the movement of a lightweight item dropped in freefall. We're using 3 data sets. First is experimental data of dropping a sponge. Take a video, upload it to Tracker, that pops out the data. And then theoretical data in GlowScript, which takes into account only gravity, no air resistance, and then another theoretical data, which takes into both gravity and air resistance. So a preview of the results is the experimental data and the theoretical data with air resistance were nearly exactly the same in both position and velocity versus time, while the theoretical data without air resistance overpredicted the motion, meaning that it resulted in velocity and position being greater in magnitude than the experimental data. So the system is the sponge, and the surroundings is the air and earth, and the initial conditions are the sponge being 3.5 meters above the air at rest when it is released, and the origin is considered to be right where it is when it's released. So here are some of the main physics ideas. We have Newton's second law, force equals mass times acceleration, where that, of course, that's net force because we have 2 forces, weight and drag. Then we have position update, where change in position is equal to velocity times change in time. And then we have velocity update, which is change in velocity is equal to acceleration times time. And then we have friction, which we're going to simplify into just k times v squared. And then these formulas make sense because using all 4 of them, we can model all the movement and motion. So for the experimental data, we dropped the sponge roughly 3.5 meters. It's lightweight, so air resistance will have an effect. We used Tracker to analyze the movement, and we made the coordinate system where it was dropped initially, and we used a calibration stick in Tracker to set the distance roughly 3.5 meters. Here is the experimental data. On the top, you can see the y graph, the y position graph, as it slowly slopes more down. And then we have the y velocity graph, which is just mostly linear down. So here's the theoretical data set with no air resistance. Looking at the code, you can see the top part is just setting up those graphs and that visual. And then once you get into the while loop, that's where it really matters. Ignore the net force. And then in velocity, we're updating it with only the gravity. And then the position is updated with the velocity and delta t. And then beneath that is just making the graphs. And then that loops for 1 second. Here's the data from the no air resistance gravity set. Of course, you can see that the position slopes downwards for 1 second, and then the velocity, it is just linear down. So for theoretical data, including air resistance, it's the same as last time, except for we found the air resistance constant to be 0.13, and we modeled it simply as force equals k times v squared because we know it's proportional to v squared. And by matching the experimental data, we found k equals 0.13. We integrated that to set the net force in the while loop, which then determines the update in velocity, which changes the update in position. So here's the data result from that. The position versus time graph slopes down, but less so than last time, and the velocity versus time actually kind of goes down, but it levels out because of that air resistance. So here's the combined data from all 3 sets. You see experimental is the highest, and then there's the theoretical with air resistance, which is pretty close to it, and then there's theoretical with no air resistance, which overpredicts the movement because it doesn't incorporate air resistance. So for the velocity y versus time graph, you see that the experimental and the theoretical with air resistance data, it is decreasing, but it's starting to level out. So it's concave up, and those are really close to each other, while the theoretical with no air resistance just keeps going linear down. After about half a second, it starts to really deviate from those other 2 data sets, and that's just because it is not calculating for air resistance. So here are the analysis questions. Some sources of error in here might be from the camera angle because it isn't perfectly parallel to the motion of the sponge. So the Tracker app might not be able to perfectly read the distance between each frame. And what does this all mean? The theoretical data with air resistance models terminal velocity at where the velocity levels out and becomes flat. Of course, in the graphs, you couldn't really see it because it cut off before then. But if it was falling for like 100 meters, you would be able to see it level out and reach terminal velocity, which is where the force of air resistance equals the force of gravity. So net force is 0 and acceleration is 0. For the what if the object was thrown downwards, then it would start with a negative initial y velocity instead of just 0. And then the velocity time graph would start at a velocity like negative 6 meters per second downward when t is 0. So it would no longer start at the origin, and the graphs would be shifted downwards. The expected and theoretical with air resistance would level out quicker because air resistance is kicking in faster because it already starts at velocity, which is what air resistance depends on. And then the theoretical without air resistance would speed up at the same rate and not be affected, other than starting at a higher initial velocity.